trust but verify. All of our discussion of correctness, integrity, and fault tolerance has been under the assumption that certain things might go wrong, but other things won't. We call these assumptions our system models. See mapping system models to the real world on page 309. For example, we should assume that processes can crash, machines can suddenly lose power, and the network can arbitrarily delay or drop messages. But we might also assume that data written to disk is not lost after fsync, that data in memory is not corrupted, and that the multiplication instruction of our CPU always returns the correct result. These assumptions are quite reasonable, as they are true most of the time, and it would be difficult to get anything done if we had to constantly worry about our computers making mistakes. Traditionally, system models take a binary approach toward faults. We'd assume that some things can happen and other things can never happen. In reality, it is more a question of probabilities. Some things are more likely, other things less likely. The question is whether violations of our assumptions happen often enough that we may encounter them in practice. We have seen that data can become corrupted while it is sitting untouched on disk. See replication and durability on page 227, and data corruption on the network can sometimes evade the TCP checksums. See weak forms of lying on page 306. Maybe this is something we should be paying more attention to. One application that I worked on in the past collected crash reports from clients, and some of the reports we received could only be explained by random bit flips in the memory of those devices. It seems unlikely, but if you have enough devices running your software, even very unlikely things do happen. Besides random memory corruption due to hardware faults or radiation, certain pathological memory access patterns can flip bits even in memory that has no faults in effect, that can be used to break security mechanisms in operating systems. This technique is known as rowhammer. Once you look closely, hardware isn't quite the perfect abstraction that it may seem. To be clear, random bit flips are still very rare on modern hardware. I just want to point out that they are not beyond the realm of possibility, and so they deserve some attention. Maintaining integrity in the face of software bugs. Besides such hardware issues, there is always the risk of software bugs, which would not be caught by lower-level network, memory, or file system checksums. Even widely used database software has bugs. I have personally seen cases of MySQL failing to correctly maintain a uniqueness constraint and PostgreSQL's serializable isolation level exhibiting write skew anomalies. Even though MySQL and PostgreSQL are robust and well-regarded databases that have been battle-tested by many people for many years, in less mature software, the situation is likely to be much worse. Despite considerable efforts in careful design, testing, and review, bugs still creep in. Although they are rare, and they eventually get found and fixed, there is still a period during which such bugs can corrupt data. When it comes to application code, we have to assume many more bugs, since most applications don't receive anywhere near the amount of review and testing that database code does. Many applications don't even correctly use the features that databases offer for preserving integrity, such as foreign key or uniqueness constraints. Consistency in the sense of ACID. See consistency on page 224 is based on the idea that the database starts off in a consistent state, and a transaction transforms it from one consistent state to another consistent state. Thus, we expect the database to always be in a consistent state. However, this notion only makes sense if you assume that the transaction is free from bugs. If the application uses the database incorrectly in some way, for example using a weak isolation level unsafely, the integrity of the database cannot be guaranteed. Don't just blindly trust what they promise, with both hardware and software not always living up to the ideal that we would like them to be. It seems that data corruption is inevitable sooner or later. Thus, we should at least have a way of finding out if data has been corrupted so that we can fix it and try to track down the source of the error. Checking the integrity of data is known as auditing. As discussed in Advantages of Immutable Events on page 460, auditing is not just for financial applications. However, auditability is highly important in finance precisely because everyone knows that mistakes happen, and we all recognize the need to be able to detect and fix problems. Mature systems similarly tend to consider the possibility of unlikely things going wrong and manage that risk. For example, large-scale storage systems such as HDFS and Amazon S3 do not fully trust disks. They run background processes that continually read back files, compare them to other replicas, and move files from one disk to another, in order to mitigate the risk of silent corruption. If you want to be sure that your data is still there, you have to actually read it and check. Most of the time it will still be there, but if it isn't, You really want to find out sooner rather than later. By the same argument, it is important to try restoring from your backups from time to time, otherwise you may only find out that your backup is broken when it is too late and you have already lost data. Don't just blindly trust that it is all working. Systems like HDFS and S3 still have to assume that disks work correctly most of the time, which is a reasonable assumption, but not the same as assuming that they always work correctly. However, not many systems currently have this kind of trust, but verify approach of continually auditing themselves. Many assume that correctness guarantees are absolute and make no provision for the possibility of rare data corruption. I hope that in the future we will see more self-validating or self-auditing systems that continually check their own integrity, rather than relying on blind trust. I fear that the culture of ACID databases has led us toward developing applications on the basis of blindly trusting technology, such as a transaction mechanism, and neglecting any sort of auditability in the process. Since the technology we trusted worked well enough most of the time, auditing mechanisms were not deemed worth the investment. But then the database landscape changed. Weaker consistency guarantees became the norm under the banner of NoSQL, and less mature storage technologies became widely used. Yet, because the audit mechanisms had not been developed, we continued building applications on the basis of blind trust, even though this approach had now become more dangerous. Let's think for a moment about designing for auditability. If a transaction mutates several objects in a database, it is difficult to tell after the fact what that transaction means. Even if you capture the transaction log, see change data capture on page 454, the insertions, updates, and deletions in various tables do not necessarily give a clear picture of why those mutations were performed. The invocation of the application logic that decided on those mutations is transient and cannot be reproduced. By contrast, event-based systems can provide better auditability. In the event sourcing approach, user input to the system is represented as a single immutable event, and any resulting state updates are derived from that event. The derivation can be made deterministic and repeatable, so that running the same log of events through the same version of the derivation code will result in the same state updates. Being explicit about data flow, see philosophy of batch process outputs on page 413 makes the provenance of data much clearer, which makes integrity checking much more feasible. For the event log, we can use hashes to check that the event storage has not been corrupted. For any derived state, we can rerun the batch and stream processors that derived it from the event log in order to check whether we get the same result, or even run a redundant derivation in parallel. A deterministic and well-defined data flow also makes it easier to debug and trace the execution of a system in order to determine why it did something. If something unexpected occurred, it is valuable to have the diagnostic capability to reproduce the exact circumstances that led to the unexpected event, a kind of time travel debugging capability. If we cannot fully trust that every individual component of the system will be free from corruption, that every piece of hardware is fault-free, and that every piece of software is bug-free, then we must at least periodically check the integrity of our data. If we don't check, we won't find out about corruption until it is too late and it has caused some downstream damage, at which point it will be much harder and more expensive to track down the problem. Checking the integrity of data systems is best done in an end-to-end fashion. See the end-to-end argument for databases on page 516. The more systems we can include in an integrity check, the fewer opportunities there are for corruption to go unnoticed at some stage of the process. If we can check that an entire derived data pipeline is correct end-to-end, then any disks, networks, services, and algorithms along the path are implicitly included in the check. Having continuous end-to-end integrity checks gives you increased confidence about the correctness of your systems, which in turn allows you to move faster. Like automated testing, auditing increases the chances that bugs will be found quickly, and thus reduces the risk that a change to the system or a new storage technology will cause damage. If you are not afraid of making changes, you can much better evolve an application to meet changing requirements. At present, not many data systems make auditability a top-level concern. Some applications implement their own audit mechanisms, for example by logging all changes to a separate audit table, but guaranteeing the integrity of the audit log and the database state is still difficult. A transaction log can be made tamper-proof by periodically signing it with a hardware security module, but that does not guarantee that the right transactions went into the log in the first place. It would be interesting to use cryptographic tools to prove the integrity of a system in a way that is robust to a wide range of hardware and software issues, and even potentially malicious actions. Cryptocurrencies, blockchains and distributed ledger technologies such as Bitcoin, Ethereum, Ripple, Stellar, and various others have sprung up to explore this area. I am not qualified to comment on the merits of these technologies as currencies or mechanisms for agreeing contracts. However, from a data systems point of view, they contain some interesting ideas. Essentially, they are distributed databases with a data model and transaction mechanism in which different replicas can be hosted by mutually untrusting organizations. The replicas continually check each other's integrity and use a consensus protocol to agree on the transactions that should be executed. I am somewhat skeptical about the Byzantine fault tolerance aspects of these technologies. See Byzantine faults on page 304. And I find the technique of proof of work, e.g., Bitcoin mining, extraordinarily wasteful. The transaction throughput of Bitcoin is rather low, albeit for political and economic reasons more than for technical ones. However, the integrity checking aspects are interesting. Cryptographic auditing and integrity checking often relies on Merkle trees, which are trees of hashes that can be used to efficiently prove that a record appears in some dataset and a few other things. Outside of the hype of cryptocurrencies, certificate transparency is a security technology that relies on Merkle trees to check the validity of TLS/SSL certificates. I could imagine integrity checking and auditing algorithms, like those of certificate transparency and distributed ledgers, becoming more widely used in data systems in general. Some work will be needed to make them equally scalable as systems without cryptographic auditing, and to keep the performance penalty as low as possible. But I think this is an interesting area to watch in the future.